Good morning, Mr. Myers here. I want to start off looking at the video key for worksheet 3D bonding types that you had last night. To start off, we're going to determine the type of bond that's formed by the electronegativity difference. So for sodium and chlorine and sodium chloride, we have 1 and 2.9. Gives us a difference of 1.9, which tells us that the bond is ionic. Remember from yesterday, we corrected our chart to say that anything from 0 to 0.3 is nonpolar, 0.4 to 1.7 is polar, and then anything greater than 1.7 is ionic. Okay, so we're going to be basing things off of that. Now that we know that sodium chloride is ionic, we can then go to the second part of the instructions, which tells us to draw the formation of the bond with the applicable Lewis structures. So sodium has 1 valence electron, being in group 1, and chlorine, being in group 7, has 7 valence electrons. And what we should ultimately see is sodium transfers or gives its electron to chlorine, resulting in the following ionic bond. Sodium with a plus charge, and then chlorine we put in brackets with the negative outside, and chlorine has its now 8 valence electrons. So each sodium has lost an electron to have an octet, if you will, with neon, and then chlorine gains an electron to have its octet full so that it is like argon. We go on to the next one. Calcium is 1.1, chlorine is 2.9. The difference is 1.8, which again suggests that it's ionic. This time we have 1 calcium with 2 valence electrons, and we have 2 chlorines. Each chlorine, pardon the bell, each chlorine has 7 valence electrons. And so we show 1 calcium electron going up here and the other going over here. In the result, we have 2 chlorines. Each has filled its octet to have a negative charge now. Calcium loses 2 electrons, making it +2. And then we have our other chlorine ion or chloride ion over here. Okay, going on into number 3. Magnesium is 1.3, while nitrogen is 3.1. This results in a difference of 1.8, which once again, like the first two, make it ionic. Okay, so to do this, we have 3 magnesiums. Each is in group 2, so each magnesium has 2 valence electrons. And then we have 2 nitrogens, and each nitrogen is in group 5, so we can indicate that it has 5 valence electrons shown. Now, if we notice, magnesium has 2 electrons, it's going to be likely to lose both of them. And nitrogen, to be happy, has 3 lonely electrons, so it wants to gain 3 electrons to have its full octet. So we can draw our arrows like this. And then this one's going to go to the bottom, nitrogen, this to the side, and this to the bottom. And so as a result, we have 3 magnesiums, each lose 2, so a +2 charge, followed by nitride, which has gained 3, giving it a -3 charge. Our second magnesium, the next nitrogen, and then our last magnesium right there. Okay, moving on to the next one. Carbon has a value of 2.5, while hydrogen is 2.1. The difference here is 0.4, which suggests that it consists of polar covalent bonds. Now, because it's covalent, we do not draw a structure like we did for the first 3. Instead, we draw our carbon. Carbon has 4 valence electrons. And then we place our 4 hydrogens around it because we've already discovered in class that carbon is going to be our central atom. So here we can see which electrons we can pair up. And so the structure that you should have shown is this one. Okay. Moving on to number 5, arsenic has a value of 2.2. Bromine is 2.8, which you cannot see. There we go. And so the difference here is 0.6. That fits within our table that we had for polar covalent. So this is, again, polar covalent. And so we have 1 arsenic. Now, arsenic is in group 5 below nitrogen and phosphorus. So it's going to have 5 valence electrons. And then we have 3 bromines that we can place around. Now, each bromine has 7 valence electrons, which I'm showing. And hopefully you can see which electrons here, here, and here that we can team up. And so we get a structure that looks like this: a lone pair of electrons on top, the bromines on all 3 sides there. Okay. Do not forget to show all lone pairs of electrons where they apply. We see up in number 4, hydrogen does not have any other unshared electron pairs around it, so we don't show it. But in 5, the bromines do have those electrons, so we'd need to show it on the Lewis dot structure. Okay, for number 6, carbon is 2.5, selenium is 2.5. The difference is 0, so this is a nonpolar covalent bond. Our central atom in this case is the one that appears the least, so carbon. So we put carbon with its 4 valence electrons, and we can put the selenium on either side. Selenium has 6 valence electrons. It's right below oxygen and sulfur in group 6. And hopefully you could see we can pair up these 2 electrons and these 2, which would give us the following. Something like this. And then hopefully you see none of the 3 atoms have their octet fulfilled yet. And so we compare those 2 electrons and maybe these 2 electrons to give the structure some double bonds. So selenium with a double bond to carbon and another double bond to the other selenium. And so this is what we should get. Okay. 2 more to go. Number 7, carbon again is 2.5. Chlorine is 2.9. The difference is 0.4. So this is going to be a polar covalent structure or polar covalent bond type. And so we've got carbon, 4 valence electrons. We can distribute the 4 chlorines around the carbon. And chlorine, being in group 7, should have 7 valence electrons around it. And hopefully what you can see here, this one's a little, let me see there, is which electrons are going to get paired together to make the bonds. And so what we end up with is something very similar to CH4 back up in number 4. This time, though, the chlorine does include those lone pairs of electrons around it. Okay. And then lastly, in number 8, sulfur is 2.4, oxygen is 3.5. The difference here is 1.1, which fits within our requirements for polar covalent. Okay. And so the central atom here is the one that appears least, and it has the lowest electronegativity, which is sulfur. Sulfur has 6 valence electrons. And I'm arranging the electrons on sulfur this way because it appears if the central atom is sulfur, that there's going to be an oxygen on either side. And so we can start to be intentional about the electron placement for that purpose. And in the process, hopefully what you identify is that oxygen here has 2, 4, 6, 7 valence electrons for each, but sulfur already has 8. And so we have to come up with a way that sulfur will still have 8 valence electrons, or maybe close to it, we'll see, and then how the oxygens get arranged. So one thought here is that these 2 electrons can combine, and these 2 electrons can combine to make a bond. And so we end up with something like this. Now in this scenario, each oxygen has 8 valence electrons. Sulfur, though, has 10. And so you might think, shoot, what are we going to do? Well, every once in a while, sulfur does this. Sulfur is an exception where it can exceed the octet. And for sulfur and sometimes phosphorus, that's okay. And that's it.